Welcome back to another Pharmacy Chalk Talk. In this video, I'm going to go over some pharmacokinetic basics. Really what I'm doing here is to give you an idea of what pharmacokinetics looks like in terms of a graph, some of the terms we use that can be found on a graph, and how those match up with the equations that we apply to different problems and case scenarios that you can see in other videos that I've posted to calculate pharmacokinetic constants and concentrations. So let's start with this graph. And so on this graph we have concentration on the y-axis and time on the x-axis. And then what we have is a depiction of concentration increasing over time until it reaches a plateau. And so this dosing scenario would be a continuous infusion, and that's because there's a nice steady constant increase until the amount of drug being cleared is equal to the amount of drug being infused in the body, also called steady state once we get there. This is dependent on your rate elimination clearance, on your half-life, and all those terms that we commonly calculate in a pharmacokinetic problem. Now let's compare that to this scenario where we can see we have concentrations that go up and down, up and down. They have highs and lows, but steadily over time it's increasing. And so what scenarios would we find this type of concentration graph with? Bolus, intermittent, and oral. And the neat thing we can see is that if we were to overlay a line that averaged out all the highs and lows of this right graph scenario of bolus, intermittent, and oral, what we see is it looks just like the continuous infusion, right? And this line here is something that we refer to as an average concentration, or more specifically when we calculate it at the top when it's at steady state, a steady state average. And so both of these graphs are considered linear graphs because we can see it does not increase proportionally with time because that's not how drug concentrations work. They reach a plateau over time, or they follow an exponential curve. And this will become important in a few minutes when I talk about why we use certain concentration calculations on an exponential curve. But let's take a closer look at one of the specific areas within this right graph of bolus, intermittent, and oral. So what we can see here is I've zoomed in on this small part of the graph where we have the following occurring. We have doses occurring at the bottom, or the mins. And then we also have different things occurring as well, including absorption and potentially distribution on the upswings of the concentrations. So if we were doing oral, then you'd have absorption and distribution. If we're doing intermittent or bolus dosing, right, there is no absorption because that's injected directly into the IV circulation. Additionally, other important points on this dosing scenario include Cmax and Cmin. So when the concentration reaches its peak, it's Cmax. When it reaches its minimum, it's Cmin. Sometimes we'll see these referred to as well as C naught or C predose. And where we see this is generally in a not steady state scenario where we want to know what is the starting or original concentration, which would be C predose, so that we know how we're building off of the previous concentrations. And then C naught is generally used when we're calculating post-time concentration. So we have to know where we're starting with a concentration to know it will end up a certain number of hours later. Finally, some other common measurements or terminology we'll see in a dosing scenario. Is the tau a dosing interval of 8 hours? So it looks like here in this example I've given you, we're dosing every 8 hours. And then we have two post-dose concentrations, C1 and C2, and these can be taken anytime post-dose, post-absorption and distribution, if that's applicable to the dosing scenario. And let's say that these two were taken at 3 hours and 6 hours. So let's recap what we have here. We have a dosing scenario that is either bolus, intermittent, or oral, where we have highs and lows, or Cmaxes and Cmins. Sometimes we refer to those as C naught and C predose. We have a tau, or a dosing interval of 8 hours. We have two post-dose concentrations that don't fall at Cmax or Cmin at 3 hours and 6 hours. And so that is a common dosing scenario we'll see. And the last thing I'll mention is generally C predose is considered to be right before the next dose. So a lot of times people will put this in equations as 8 hours. Now let's zoom in one more time and take a look at what we would call the linear portion of this graph. And so it looks very similar to our graphs above, except for you can tell the y-axis with concentration looks a little bit different, and that's because it's this, a log linear graph. So it makes it look linear so that we can do calculations based off of it. Now let's label a few more things here from our original graph here on the right. And what we can see here is we have a C max or a C naught, depending on the situation we're talking about, the two post-dose concentrations, so C1 and C2, and then the C minimum or C predose, and then another dose, and so on and so forth. Now, why is it important that we plotted this drug concentration time relationship on a log linear graph? That's because it lets us do all those concentration and PK parameter calculations that we've gone through in other videos. So let's see what that looks like. What about the slope? What is a slope in this situation equal? Well, we can remember that rise over run is slope, and so rise over run in this situation, and it's a negative because it's going down, there's a negative relationship, right, is your rate elimination rate constant. What else can you calculate from this graph? We could calculate a T1 half, either graphically or from this equation. And then one tip here is, where does this 0.693 come from? It comes from the fact that the natural log of 0.5, or a half-life, is equal to a negative 0.693. And so when you work out the equation with a negative 0.693 and a negative KE, it turns into a positive to calculate half-life. So that's a fun fact. Where does the 0.693 in half-life come from? It's because it is half the drug concentration that is then turned into a positive 693 by the negative rate elimination rate constant. Finally, what happens when we have a drug here in the middle? What calculations do we do to calculate future concentrations or previous concentrations? Well, let's start with a future concentration. Again, if you go to my other videos, you'll see I do this in detail, but what we do is we would multiply whatever this concentration is here, concentration nu, times the exponent to the negative rate elimination constant times time. So again, we're able to do math on this log linear graph, manipulating the slope, which is the rate elimination rate constant, and exponents to calculate future concentrations and to calculate previous concentrations. Now, what would a previous concentration look like in this scenario? That would look like this, where instead of multiplying it by the exponential of the negative rate elimination constant times time, we're dividing it by the exponent to the negative rate elimination rate constant times time. So I hope you can see how we've gone from a normal linear graph that has an exponential increase in the drug concentration, how we label different Cmax and Cmin and post-dose and pre-dose concentrations based on a bolus, intermittent, or oral dosing scenario. And then finally, how we utilize the benefit of a log linear graph to then calculate the slope, which is the elimination rate constant, half-life, which is based on the elimination rate constant, and the natural log of 0.5, and how we would calculate future and past drug concentrations based on a known drug concentration by multiplying or dividing by the exponent that includes the negative rate elimination constant in time. Thank you for your attention.